So, welcome everyone on the third event of the webinar series of the European Meteorological Society. I am Monika Lakatos, the president of the Hungarian Met Society, one of the organizers of the webinar series, together with Martina Junge, the executive secretary of the EMS, Vesna Juricic, the president of the Croatian Met Society, and Ernesto Rodriguez, the president of the Spanish Met Society. We are organizing this serial together. First, we go through the formalities. So please note that the webinar will be recorded for later publication on the EMS channels. The second is that you can ask questions by typing into the chat after the two talks are finished. The chat only be seen by the panelists who are speakers and the organizers. If you want to speak anyway, please raise your hands. So let's go further with the program. We have two speakers on today's program, Árpád Kis from Hungary. He will speak about the theory of the geomagnetic storms in about 20 minutes, and Hanneke Luijting from Netherlands. She will give a few insights on photography of Aurora Borealis in about 5 minutes. I would like to introduce shortly our speakers first. Árpád Kis received his PhD in 2005 from Ludwig Maximilian Universität München, Germany, based on the research work performed at the Max Planck Institute für extraterrestrische Physik in Garching, Germany. His main research focuses on near-Earth space plasma processes and energy dissipation, which are subjects of vital importance if you want to explain space weather phenomena. He is a senior research fellow at the Institute of Earth Physics and Space Science, Sopron, Hungary, and the leader of the Space Research and Technology Research Unit. He designed the concept of the Hungarian Space Weather Data Center, which provides space weather-related data in real time. He is a member of the Scientific Council of Space Research and advisor of the Hungarian ESA delegation. In recent years, he focused on the potential impact and risk of space weather events on society and critical infrastructure, and investigated the possibility and methods of preparing against them. Our second speaker will be Hanneke Luijting from Netherlands. She did her master's degree at Wageningen University, followed by a PhD in meteorology at the University of East Anglia in East England in Norway, in the UK. After that, she worked at the Norwegian Meteorological Institute for 8 years, the first 6 years as a forecaster in Tromsø, and the last 2 years as a researcher in Oslo. Now she is back in the Netherlands and have basically changed her career. She works for the government as a sustainability advisor, focusing on the circular economy. This is something she always been passionate about, and she thinks witnessing climate change firsthand, especially in the Arctic, is what made she even more keen to work towards a more sustainable future. So I would like to give the floor to our first speaker, Árpád Kis. So Árpád, please share your screen and give your presentation. Thank you.
Yes, thank you very much, Monika. A very warm welcome to everyone who is joining this webinar. I am sharing my screen, so just give me a few seconds, please. Please let me know if you are seeing the slide.
It works.
Okay, fine. So I have about 20 minutes, as it has been mentioned by Monika. So I would like to give a general overview about the geomagnetic storm, which is can be a source of beauty, and also it can be very nasty. So let us begin. So Everyone knows that without the sun, life on Earth would not exist. It provides heat and light for us, it drives ocean currents, climate, season changing, weather, and makes plant life possible through photosynthesis. And also it makes our life possible. But this is not the full picture. So if we take a look at the sun from another perspective, the sun is also a source of many, many harmful effects, for example, radiation like X-ray or gamma ray, energetic particles, just to name a few. And this is the bad news. But fortunately, we all live on a giant and strong magnet, and which is the Earth. And that is a cool thing because that is the second factor that makes possible for life to exist on Earth. The extended magnetic field, which what we call the Earth's magnetosphere, provides a very effective protection against the many effects coming from the sun. The Earth's magnetosphere stands in front of our planet as a huge umbrella, as you can see from the picture, and this is shielding us from the harmful effects of radiation and energetic particles coming from the sun. So the sun is constantly emitting material from itself, which are mainly protons and electrons in a state known as plasma, collisionless plasma, to be more precise. This is the so-called solar wind. So basically, this is a constant flow of particles coming from the sun, and the solar wind flows with an astonishing speed. It's near the Earth, around this region, the velocity of the flow normally is between 400 and 600 kilometers per sec. That is quite a wind, I think. But the solar wind cannot penetrate the extended magnetic field of the Earth, the magnetosphere. So it is slowed down, as you can see here, and it's forced to flow around it. Now, if we take a look at Mars, we are talking a lot about Mars today. We can estimate, not today, I mean nowadays, we can estimate that what would happen if our planet, to our planet, if the magnetic field would disappear. Because there is evidence that once Mars had a quite similar magnetosphere as Earth. But something happened and the Mars magnetic field disappeared. We see the consequences of the missing Mars magnetosphere. So the solar wind is eroding the atmosphere, which is already thin. The surface is subject to radiation and harmful energetic particles. So it's not a really good place to be. So to conclude, we are in a very lucky situation. So we can enjoy the beautiful benefits of the sun, light and heat, without the harmful effects due to our extended magnetosphere. Our planet is very unique and a precious place, so it's worth protecting it. So we can say that everything is fine. We can sit back, relax, have a nice coffee, something, maybe even a drink or tea, maybe what we prefer, and maybe listen to the music also. Well, this is valid for most of the time, but life is not so simple. So if we take a look at the sun with the naked eye, the sun seems to be the same always, but this is not true, because the sun does not behave the same way all the time. So if we grab a telescope and take a closer look at the sun, as Galilei did in around 1600, we can observe the sunspots. This picture that you can see is provided by SOHO spacecraft. So if you go to the SOHO webpage, you can have real-time images of the sun. It's for free. You can download it in multiple bands. So this one, as you can see, I downloaded it yesterday. So the sunspots are black holes. I mean black regions, not luminous regions on the surface of the sun. We found out quite early that the number of sunspots shows a periodicity of about 11 years, which is a sign of solar activity level. That is what we call the solar cycle. So we have a periodical change in the solar activity, varying from solar minimum and solar maximum, which is expressed in minimum sunspot number and maximum sunspot number. During the solar maximum, typically we can observe more frequently violent processes on the surface of the sun. So think about solar flares, which are bright flashes on the surface of the sun if we take a look at them. and also the CMEs, or coronal mass ejections, what we are focusing on today. So what is a CME? The CME is an explosive burst of solar plasma that is launched into the space, as we can see also from the SOHO picture. This is a nice CME, coronal mass ejection, and it got even a name. It's the light bulb CME. It's a famous one. So this plasma cloud contains charged energetic particles and moves with thousands of kilometers per second. As remember, this is faster than the solar wind speed, so it overtakes the solar wind speed. Now, if this cloud hits the Earth's magnetic field, the magnetosphere becomes compressed, obviously, especially in this region. The magnetosphere and the solar wind under normal conditions are in a dynamical equilibrium. So the magnetic force stands against the pressure of the solar wind flow. But in the case of the CME, the magnetosphere suddenly is faced with a substantially larger pressure, or we can say that the magnetosphere is getting hit by this fast-moving plasma cloud. So the consequence of this is that the consequence of this process is the geomagnetic storm, or as we used to call it in science, the geomagnetic disturbance. So what does this mean? It means that the geomagnetic field is suddenly quickly changing in intensity, direction. For example, and fortunately, we have many geomagnetical observatories all around the Earth where we can measure the geomagnetic field very accurately, and we can follow what happens during a geomagnetic storm. Here in this figure, we can see the registration of the DST index. The DST index, or disturbance storm time, is an index which shows the geomagnetic activity, which is derived from a network of near equatorial geomagnetic observatories. So it is a planetary index. And as you can see, we have at the very beginning, we have a small jump in the magnetic field value. This is the so-called SSC, or sudden storm commencement. This is effect of the strong compression of the magnetosphere, so we have an increase in the intensity. And then we have the so-called main phase, which where the DST drops rapidly, as we can see here. This is the main phase. And after that comes a usually longer, not so fast changing time period, the so-called recovery phase, when everything is going back to normal. This recovery phase can last from hours to days, depending on the strength of the geomagnetic storm. Also, we have a K index. If you would like to take a look at what does this show and how they are calculated, please, you can take a look. But now we would like to, it's just a few words that the DST index and the K index is basically which quantifies the disturbance, especially the K index, and the DST is also very nicely used if you would like to hunt for geomagnetic storms. Now, the compression of the magnetosphere is not only happening on the day side, but also it is compressed on the night side. So what we call in the magnetospheric tail. Basically, what we can say that, as you can see, the magnetosphere structure is like a comet. So it goes way. It's like in the tail, the magnetic field lines are going very nicely far away, and as you can see, the magnetic field lines are going in one direction on one side, and they are going into another direction in the north and the south spheres, and sometimes they can get very close together. So basically what we can say that the interaction of the magnetosphere with the CME plasma cloud can change the structure of the magnetosphere, leading to multiple effects. So in the magnetospheric tail on the night side, we can see that the magnetic fields, as I mentioned, they are extended far from the Earth, and these fields line opposite in direction orientation. So due to the pressure, these oppositely directed magnetic fields can come very, very close to each other, and when they do so, a magnetic reconnection can take place. So what is a magnetic reconnection? So we have this magnetic reconnection occurs when we have magnetic field lines in opposite direction, and to put it simple, they touch it, they merge, rejoin, and they snap apart, releasing a large amount of energy to heat plasmas and to drive higher speed outflows, as we can see in this picture. So here is the reconnection, and this line is connected to this one, and then it's like a slingshot. It sends particles, it sends a jet away. And it sends, it sends, as you can see, in the Earth's direction, these accelerated particles, electrons. It's like really like a slingshot. Since these charged particles, they can move only parallel to the magnetic field, because this is how the physics is made. And if we follow their path, this is where we end up. We end up at the polar cusp. So this is the location where the particles can penetrate into the atmosphere by following the magnetic field lines. And this is how the aurora, or the northern lights, are produced. So the accelerated particles, when they come at lower altitude and the atmosphere is getting denser, they are colliding with atoms and molecules of the atmosphere and excites them. And therefore, these atoms and molecules are acquiring, or they come to a higher energy state. And when they are getting back to normal energy level, they release a photon, and that is the northern light that we observe. This is happening around between 100 and 400 kilometers altitude. And typically from oxygen atoms at 100 kilometers to 200 kilometers at altitude, the light emitted is typically green or yellow, whereas at higher altitudes, above 200 kilometers, the emitted light is more often red. So occasionally the lower edge of the aurora will have a pink or dark red fringe, which is produced by nitrogen molecules at altitudes about 100 kilometers. But nitrogen generally gives off a blue light. Now, what is important to mention, let me go back just here. It is important to mention that the solar wind particles or other particles coming from the sun are responsible for the aurora. Not the solar wind particles are responsible directly for the aurora, but particles that have been accelerated in the reconnection process, and which took place as a consequence of geomagnetic storm. And this is how basically the auroras are formed. Okay, so it's a nice question that, okay, now why do we care about geomagnetic storm? Scientifically, it is interesting, of course, but and also it is important, but is there anything else? And well, the answer is yes. We have a lot of things. If we take a look at this figure, which summarizes basically all the effects related to what we call space weather, and the geomagnetic storm is one type of space weather storm, a very important and very dangerous one. So what can be the consequences of a geomagnetic storm? Well, let's see. Rapidly changing magnetic field, as we learned in school, induces electric current. Now, this is how the generator works. We rotate the conducting frame in a changing magnetic field. In the case of the Earth, we have two conducting layers. The ionosphere, as you can see here in the picture, and we have also the Earth's crust. This is where the changing magnetic field during a geomagnetic storm can induce very strong currents. So if the ionosphere is disturbed, the radio communication can be disrupted. Especially the HF, the high frequency band, is affected, and this is really a problem because aviation, military, and governmental agencies use this HF band for communication. But also communication with spacecraft satellites can be disrupted because the signal has to go through this disturbed ionosphere. And this can lead to data loss and obviously GPS, so the local the GPS is also can be affected, so it becomes unreliable, the geolocation. Now, if you think about it, a sudden and severe disruption in communication, especially in these troubled times, well, we know what is happening today, it is might be very scary and even dangerous. Geomagnetically induced currents, and this is now we are going to the Earth crust, can attach to man-made large metal structures like high voltage power lines, railways, oil and gas pipelines, underwater communication cables, and so on. Basically everything that stretches over a long distance, as you can see. So the presence of GICs in these systems can cause multiple problems. And this is not some science fiction and scare tactics, and this already happened several times before. For example, it's I think 13th of March in 1989 in Quebec, in Canada. During the night, geomagnetically induced currents caused severe damage in the system, the power lines, and the failure of an important transformer station. So as a result, about 7 million people were left without electricity for about, if I remember correctly, 9 hours. The reparation of the system took several weeks, and basically the whole network was affected. They signaled malfunctions basically in all the North American continent. And even if we go to 2003, and there was a series of geomagnetic storms, and they are so famous that they really got the name of Halloween storm, because it happened around October 30th and 1st of November. And this is really is a school example of the various effects that can take place during the geomagnetic storm, because we had problems in communication. About 20 satellites were there were some malfunctions. Even one, I think, Japanese satellite has been lost completely. About half of the NASA satellites has been affected. And for example, the LORAN, the Coast Guard, the U.S. Coast Guard, had to shut down the navigation system, their own navigation system, and the climbers in Himalayan region could not doing communication with their satellites, mobile phones. But the biggest geomagnetic storm event was the famous Carrington event, which was, I think, 1859, which was the largest recorded geomagnetic storm in the history. So people could it was a very interesting event, because people could read their newspapers in Cuba during the night due to the presence of northern lights that were visible over the island. So there was no modern technology at the time, only the telegraph and the telegraph wires. And these geomagnetically induced currents were attached to the telegraph cables, which led to failure of the system. So because we have reports of electroshocked persons, buildings caught fire, and so on. Now, what would happen if today a strong geomagnetic storm would hit the Earth? There are many studies and model calculations related to that, and we can say that they estimate substantial damage and disruption in economy, in critical infrastructure, in logistics, communication, and obviously problems in society. So we can imagine a highly populated area or a large city where all of a sudden there is no electricity, no water, no communication, and the situation can last for hours, days, or even weeks, depending on the cause damage. This is not a very good scenario, so we have to make steps to be prepared for such events. Okay, we might ask that how is that possible that in the 21st century we are living in a modern and well-developed technology-based society? We have to face these problems. The answer is ironically simple, because we live in a modern and well-developed technology-based society. The technology we are using, and which becomes more and more refined, that we are using in our everyday life, they are vulnerable to space weather effects and vulnerable to geomagnetic storms especially. So obviously, we are aware of the problem, and a huge effort is made globally to understand space weather and to develop methods and standards to be protected against them. But it takes time, and we just started our journey in this direction. But okay, we are working on the problem. And just some final words, maybe. The purpose of this presentation was to provide a general understanding of the geomagnetic storm phenomena touching the Aurora question. The provided picture is far not complete, and there are many, many details and aspects that were not mentioned intentionally because and we did not enter into details. So please consider it as a quick snapshot of the problem and nothing else. So this concludes my talk, and I really want to thank you very much for your attention. And I give back the screen.
So thank you, Árpád, for this very interesting talk. I'd like to remind the attendees that you will have a possibility to ask questions after the Hanneke presentation to any of the presenters. So, Hanneke, the floor is yours.
Thank you, Monica. I will also share my screen. Let's see. Is it working?
It's excellent.
Thank you. So I'm going to talk briefly about the beauty of the geomagnetic storm and capturing the Aurora Borealis in photos. So my name is Hanneke, and I was lucky enough to live in Tromsø in northern Norway for 8 years while working at the Norwegian Meteorological Institute. So I was lucky enough to see the Aurora many times. But actually, the first time I saw the Aurora was not in Norway, it was in the Netherlands. And this is actually, I think, the Halloween solar storm that Árpád was mentioning. This was late October 2003 when there was... So if you're listening and you think I don't live at the right latitude to see the Northern Lights, you might be surprised. This was during a solar maximum, and the Aurora was seen as far south as the Mediterranean. But in general, to take photos of the Aurora, what you want to do is check the weather and the Aurora forecast. There are many websites that predict how active the Aurora is going to be. Find a dark place. If you're not in the northern Norway, for example, you need to have a clear view of the sky towards the north. In Tromsø, this didn't matter because the Aurora was usually overhead and it could be in any direction. And you need a lot of patience because often you're waiting during the dark night and waiting for it to show up. And sometimes it never does. And sometimes suddenly the whole sky is full of color. The preferred equipment for taking photos is an SLR reflex camera, a wide-angle lens, and a tripod. I'm very quickly going to go through the technical details. You put your camera on manual mode if you have that. Put the focus on infinity. Use a wide lens so you catch as much light as possible. Wide lens opening as well. Use a shutter speed of 5 to 25 seconds. It depends a bit on how bright the Aurora is and how fast it's moving. If you use any more, the star will become trails. The ISO you can set to something between 400 up to 3000. This depends a bit what your camera can handle without it getting noisy. And I always use the remote to, even when the camera is on a tripod, because pressing the shutter button can also shake the camera. But if you don't have a camera like this, smartphones capture Aurora really well these days. When I was still living in Tromsø, this was not a possibility. but now I see people taking amazing pictures with their smartphones. So the next tips are just something you can use whether you use an SLR camera or your phone. One advice is the full moon is not a problem. People often think that a bright moonlight, they might not be able to see the northern lights, or it's not very good for taking photos. I actually loved it because it lights up the landscape and it becomes more like daytime. You can take really nice photos like that. Sometimes it is a problem though, if you have to photograph straight into the moonlight, you get a strange star in your sky. And here actually you can see on the bottom of the bottom of the green band, you can see the pink fringe that Árpád was also talking about. Especially when the northern lights are moving very fast, you can see this pink at the bottom. It's really pretty. And I said, look for a dark place, because if you have a lot of city lights, it can be disturbing. But if there's strong aurora, it's actually really nice if you find a viewpoint and have city lights included in your photo. And also dark starry nights are really nice too, of course. But sometimes it can be too dark, so you don't want to be somewhere where there's absolutely no light. At least for the photos, it's not the nicest thing. This photo is special to me because in Tromsø we didn't see the red aurora very often, because as Árpád also says, that's higher up, and in Tromsø you're usually underneath the band of aurora, so you get only the green. And here was a rare occasion where we saw it was actually much further south than Tromsø, so we saw the red on top as well. But because here it's cloudy, there's no moon, there's no snow on the mountains, and it's windy, so there's the fjord here, but it's not reflecting any light because it's too windy. It doesn't make for the best photos. So what I always try to do is try to find an interesting foreground to include. When you see the aurora for the first time, it can be very tempting just to take a photo of the sky to have proof that you've seen the northern light. But if you treat it like a normal photo and look at the composition and try to include something interesting in the foreground, you get much better photos. And especially when the aurora doesn't fill the entire sky, it doesn't always do that, then it's nice to have something else to show. In Norway, we're lucky enough that you're always near the water. So if you have the fjords, the sea, a lake, and it's a very calm night, you can use the reflections to take very nice photos of a double aurora, basically. And you always have to be prepared, because northern lights, you don't always know how they're behaving. So in the photo on the left, for example, suddenly the strongest activity was over my head. So you have to turn your camera from taking a landscape photo to a portrait photo. It's not always very easy when it's on a tripod. And the photo on the right is taken at 5 in the afternoon. It was still light, and the northern lights were already active. So you never know, they can show up at unexpected times. And sometimes you're taking photos in one direction and it's suddenly behind you. Another thing I love to do is get creative. This is a photo where I noticed there was not only lights in the sky, there were lights in the sea as well. You see the blue dots in the water. It's bioluminescent, either plankton or algae. I'm not a biologist, I don't actually know what it was, but it was very nice to try and get both phenomena in one photo, the lights in the sky and the lights in the sea. My last advice is don't forget to enjoy the northern lights without your camera, because it's really something else to see it for yourself. You can look at really beautiful photos, but the way it's moving, it's really magical. So take a moment without the camera as well and enjoy. Thank you. That was my very short presentation.
Thank you very much, Hanneke, for sharing us with these amazing photos.
Thank you.
So thank you. And also you shared some technical details. So thank you. Maybe we will have more chance to get Aurora in the
Yes,
future.
I hope so.
So thank you very much, both speakers, Árpád and Hanneke, to sharing with us their knowledge about the geomagnetic storms and Aurora Borealis. So it's time to ask questions to our speakers. So I am asking Vesna if there is any question in the chat now, or if not yet, I have one to Árpád first. So there was a strong geomagnetic storm in 23rd of March this year. And I've read on the internet that possibly we reached the solar maximum, but it was awaited only for a year later. So what is your opinion on this statement? Do you think that, or if you want to estimate the solar maximum, what kind of error can we make it?
Oh, to predict something, it's very sometimes it's very tricky. But let me go back to my presentation, if you allow me to share my screen.
Please try that.
Because I think I have one figure that is included
In the first part, maybe.
Yeah. Here, yes.
Yeah.
So here I did not mention, and thank you for asking that. The red line here, it is basically a prediction, or the prediction. So according to that, it's I would rather expect it to reach the solar maximum in 25 or 26 or around that. But as you can see here, we have, well, this is the data, and this is what we have. So it's I don't know. It's hard to say. I think it's much easier to say it afterwards. But basically, we are around the solar maximum. So this is a good time to make measurements.
Thank you for your answer. And I'm asking Vesna if there is any question.
Yeah, for the moment, it's not a question, it's more comment from Friedrich Wallach. He said for Dr. Kis, I'm happy to hear that there are the charged particles, electrons, from the geomagnetic tail that are primarily responsible for exciting the atmospheric particles and producing light of the auroras. Many times I hear from people that the auroras are caused by solar wind particles, which I believe is not right, or rather it's too oversimplified. Thank you for the nice presentation.
Oh, thank you for the comment. I think that it happened many times in the news that auroras has been referred as a solar particle to be responsible for the auroras. So they are it's not very. So basically, solar particles can excite also the atmosphere, but most of the time we cannot see them because it's happening on the day side. So the aurora, as we mentioned, they are really produced from physical processes that take place in the magnetotail. Thank you very much.
Thank you for reflection.
Now we have a question for Hanneke from Ernesto Rodriguez. Can you further comment on the speed of evolution of aurora structures?
Yes, it's really variable. Like sometimes you will see a green band of aurora that hardly moves, or sometimes it will ripple a bit like a curtain in the wind. And sometimes it moves so fast that you can hardly follow it with your eyes. It goes really fast and all over the place. So it's really difficult. Like it really varies, and that's something that you cannot capture really well in photos. So that's why I think like seeing it in real in front of you is a really special experience.
Thank you.
Thank you, Hanneke. So Vesna, can you see more questions?
Not at the moment.
I have one to Hanneke. What was the most southern place where you captured Aurora in your lives?
The most
southern in the geographical coordinates.
in the Netherlands. The Netherlands was the most southern. Like, it's quite special because I lived in Tromsø and I also spent 6 months in Alaska. But still, the first time I saw it was in the Netherlands. So that it was just before I was leaving for Alaska, and it was really special to see it in my own country. It's quite rare.
Yes, thank you.
Árpád, do you want to say something?
Please.
Yes, I would like to have a question to Hanneke. How many nights did you spend looking for auroras? Percentage-wise, while in Tromsø.
It was actually funny because I lived in Tromsø for a long time, and I think it took about 5 years before I finally said sometimes like, oh, tonight I'm tired, I'm staying home. Because I found it so magical that if there was forecasted aurora and there were clear skies, in Tromsø you don't always have that. So you get some breaks with bad weather, but if the weather was right, I usually was out and I wanted to watch it. So it really took 5 years of seeing it. Like during the winter time in Tromsø, you can see it every other night if you're lucky. So
wow.
Yeah, I've had a lot of sleepless nights.
Very nice, thank you.
We have another question from Sylvain Geoffrey. About the color of aurora due to the molecules and atoms encountered, how can you explain the motions of auroras like curtains in the wind?
Oh, maybe I should answer. Yes, okay. I try. So basically, it's I think as it is a consequence of the processes of, as I mentioned, the structure of the magnetosphere is changing during the geomagnetic storm. So it's a kind of fluctuation you can expect, and I think this is what we can see, this motion or curtains in the wind. It's like it's a change in time of the amount of particles which are coming in, and also the slow motion of the magnetic fields. It's a combination of the both. This is how I think I can explain that.
Thank you.
I have a question to Hanneke regarding the ChatGPT. So if you see photos, a real one and made by ChatGPT, can you make difference based on your expertise? What do you think?
Oh, that's a difficult one because I think it's getting better and better the way it's. I mean, it bases this on photos it finds on the internet, I guess. But what you do sometimes see is people taking a different foreground and putting aurora on top of it, and sometimes you can see it's fake, but some people do it really well and it looks good. It's hard to see the difference, I think.
And another question for you from Ernesto Rodriguez. Can you comment something on the forecasting of solar perturbations and their effects?
So just to so about the forecasting of space weather phenomena, I think is the holy grail of the whole science, and this is what we really would like to achieve. But it seems that we are really far from that. But in the case of geomagnetic storm, we are in a lucky situation because we have a spacecraft orbiting between the Earth and the Sun, like the SOHO and ACE. And they are looking at the sun, and they are measuring the plasma. So if something is happening, we can have real-time data provided by them. This is a cool thing. And so in the case of geomagnetic storms, we are able to see it before that. And this is, if you take a look at the NOAA and the KP index or the European Space Agency forecasting, I think mostly they are relying on data and obviously models also. But I think there is another direction forecasting these events is to take a look at the evolution of sunspots and how they change or how they evolve and how they can be transformed into flares or CMEs that they are source of these events. So this is another direction which is studies going on. But I think basically it's like I used to say that we have a like in the case of the earthquakes, we know that it will happen, so we have to be prepared. So we need to have standards and some technologies to be prepared. At least
Thank you.
Until we cannot forecast them. Thank you.
Thank you.
Thank you very much. So Vesna, can you see more questions?
No, right at the moment. Anybody else from the audience? Do you have any questions or are interested in something?
Nevertheless, you can send an email to our speakers after the webinar. So I would like to thank especially for Árpád and Hanneke for their very interesting presentation. I learned a lot. Hope that the audience think the same. So thanks for everyone attending the meeting, and I would like to invite you to submit ideas for the further topics and speakers. You can send an email to EMS Secretariat, for example, regarding these new topics. So we would like to keep these webinars interesting and well visited. So thank you very much, everyone, and see you on the next event. We will inform you about the next event. So thank you very much, all the organizers as well. Thank you.
Yeah.
Thank you.
Thank you for the opportunity. Thank you for being here. Thank you.
Thank you.
Yes, thank you for inviting me.
Thank you. Thank you very much. Bye-bye.
Bye-bye.
Yeah. Goodbye.
Bye.